Welcome to Teddy Talks. In this video, we're going to look at another numerical problem that is to do with the lift problem. Now, they say a body hangs from a spring ballast suspended from the roof of a lift. That the lift has an upward acceleration of 2.5 meters per second squared and reads 60 newtons. What is the weight of the body? 2. Under what circumstances? Under what circumstances will the ballast read 40 newtons? What would be the ballast reading if the cable of the lift breaks? So let us ask our question, and we are going to begin by sketching. We begin by sketching that this is our lift, this is the spring ballast, and this ballast of ours, that is our spring ballast. So there is a body that is hanging, whose weight we know mg acts downwards, and there is a normal reaction R, which is the same as the tension in the string, and it is the tension in the string that is the ballast reading. That one you should be knowing. The tension in the string is the reading that we see from the ballast. They are saying, what is the weight of the body? Now, let's read the question. A body hangs from a spring ballast supported from the roof of a lift. The lift has an upward acceleration. So this one means that our lift is moving upwards. Now, if the lift is moving upwards, what does it mean? We say that the tension in the cable should be greater than the weight of the body. So we can quote and say that for upward motion or acceleration, the tension in the string should be greater than the weight mg. Now, this means that the net resultant upward force, which we said is given by MA, will be equal to tension in the string minus mg. The tension in the string is the reading of that is the reading of the spring ballast. So it means that my MA here is equal to T minus mg. Now, what do we know? We know that, we are seeing that the tension in the string is equal to MA plus mg. Now, on further calculation, we say the tension is the reading on the spring ballast. Therefore, 60 is equal to m into A, which is 2.5 plus 9.81. Now they wanted weight, and we know that weight is mg. Now if weight is equal to mg, what does this one tell us? It tells us, one, they never gave us the mass of the, we don't have the mass of the lift. So we have to first get the mass if we must get the weight of the body. So 60 is equal to 2.5 m plus 9.81 m. So we get our calculators. This is 2.5 plus 9.81 gives me calculator, let me reset it. 2.5 plus 9.81. 2.5 plus 9.81. 16 is equal to 12.31 m. So we compute the value of m. 60 divided by Arthur. M is 4.8741 kilograms. But we know that weight is equal to mg. So this is 4.8741 times 9.81. So from this expression, we are supposed to get our weight, and it gives us 47.841 newtons. So that is the weight of the body in the lift. That one should be equal to the weight of the body in the lift. This is the actual weight, not apparent weight. Now let's look at Roman numeral 2. Roman numeral 2, they are saying that under what circumstances will the ballast read 40 newtons? Now for this question where they're asking when, under what circumstances is the body going to read the 40 newtons, they want to tell us when will the tension in the string be 40. Now here we can write and say that for the ballast to read 40 newtons, comma, this means that the tension in the string is 40 newtons. Now, you realize, one, we know the mass of this string, but we do not know the acceleration in this case. Now, for this string to read 40, assuming we are still considering the upward motion, 40 newtons should be equal to MA plus mg. So our 40 is equal to 4.8741a plus this is 47.81. Therefore our a, we calculate for the value of a here. When we calculate, when I press my calculator, what do I get? When I press that value on a calculator, 841, it shows me that the acceleration is negative 142 meters per second squared. So under what circumstances, what does it mean that we conclude and say that the ballast, the spring ballast, will read 40 newtons when the lift is retarding, at 1.614 meters per second. So that is the scenario where we can see that the lift is doing what? Is decelerating when it is moving downwards. Why we say retarding? Because we got a negative acceleration from this expression. Then another thing they asked, what would happen? What would be the ballast reading? What would be the ballast reading if the cable of the lift breaks? Now, members, when the cable of the lift breaks, what happens when this cable breaks? It means the lift is moving at the acceleration due to gravity. And if the lift is moving, it is falling downwards at the acceleration due to gravity, it means that the apparent weight or the reading will be 0. So the ballast reading will be 0. We're going to say that the ballast reading will be 0 since the lift will fall at will fall due to acceleration due to gravity. So that is the reason. That is the reason we could do. That's the reason we give, and the reason is that we are getting a 0 reading. Why? We are getting a 0 reading simply because the lift is moving downwards at an acceleration that is equal to gravity. If you remember, we said that the resultant force for a body moving downwards is m into g minus a. Now, if g is equal to a, this minus this gives us our r as a 0, and therefore our reading will be 0 on the spring ballast.